Hello, everybody. Welcome to the global live streaming of the major changes to the 2024 edition of NFPA 70E. I'm Jim Phillips, and once again, we get to go through that time-honored tradition of transitioning from NFPA 70E. This time, it's the 2021 edition into the 2024 edition. We have quite a bit that I'm going to try to get through in this hour together, and we have such a crowd online. This is fantastic. We have 24 countries that are represented, which I think is really neat because that means that NFPA 70E has a tremendous global reach. In fact, I just returned a couple weeks ago from an international, basically training where I was in Europe and Australia, New Zealand, all over the place, teaching, among other things, NFPA 70E as well as IEEE 1584. Before we begin, I need to cover a couple of things. And number one is what is going to happen here. It's going to be based on my thoughts, my opinions. It does not necessarily reflect the opinions of any of the various standards organizations. And this is really important because I'm very, very involved with many of the different standards organizations and hold some pretty key positions with a few of them. And also, please do not record or copy this material. So moving from 2021 to 2024, it took quite a bit of input, 357 public inputs. Think of those as like proposals, which led to 166 first revisions. And then for the second draft, there were 168 public comments that then resulted in 73 second revisions. I'd like to thank, so many people, the NFPA staff, the various NFPA 70E committee members, all the people that provided the public input and the comments. This revision cycle was a bit interesting. The closing date for the public input was June 1st, 2021. And then we had our first draft meeting where we review the public input, except because of the pandemic, it was virtual. And then the second draft, the closing was May 31st, 2022. And then we had our second draft meeting in Kansas City last summer. That led to the second draft report. And then we had what are referred to as NITMAMs, Notice of Intent to Make a Motion. If you have a copy of the 2024 edition of 70E, fantastic. If you have not obtained a copy yet, take a photograph of this page right here. There's a link that NFPA has where you can actually go to a viewer and you can view the 70E. You can't copy it or cut and paste or anything, but at least you can view it online. There's also what's known as a style manual, the NEC National Electrical Code Style Manual. And some of the changes that have occurred this time, as well as previous editions, are trying to obtain conformance with the requirements in the style manual. With every new edition, there are global changes throughout the entire document. And one such change is with shock, which is now electric shock. Because what happens is the word shock, it's got a lot of different meanings. Are you surprised? Is it a shock wave? What is it? So this is to differentiate between all the variations of shock and the electric shock. So now we use the term electric in front of shock, electric shock. But there are some exceptions, two exceptions actually. There is what is known as a hearing protection boundary and a lung protection boundary. Both of these terms use the word shock. In these cases, they're referring to shock wave, not electric shock. So now, places where you see shock risk assessment, it now says electric shock risk assessment. Anywhere you see shock, you see it preceded with the word electric, except for the two exceptions. Electric shock appears 63 times in the 2024 edition. So this was quite a sweeping change within NFPA 70E. Now, there was another change, and this has to do with an ASTM standard. There's a newer ASTM standard that came out in 2021 that is for protectors. And protectors, what this is all about, it used to be referred to as leather protectors, but because of this new standard within NFPA 70E, the word leather has disappeared, and they are just simply referred to as protectors. Another change. Each article within NFPA 70E is required to have a scope. Believe it or not all of them did have a scope, and the scope will always be .1 of each article. So scopes were added to these articles here. There were scopes already for these articles right here. So now each article is going to have a scope. Article 90, there were some changes made to Article 90 moving from 2021 to 2024. And what we have is in 2021, 90.1 was the purpose, which is now a problem because .1 has to be the scope. The scope was in .2. And then we have the standard arrangement. That's just showing you how 70E is laid out. And then we have the mandatory permissive rules and the explanatory material. Well, now in 2024, scope had to move to the first position, 90.1. And in the scope, there were references to what is covered and what is not covered. That was removed from the scope, and it now follows purpose. It has its own section, 90.3, workplaces covered and not covered. And then we have the standard arrangement following, and then the mandatory permissive rules and the explanatory material. The explanatory material, there was new language added here, and it has to do with when other standards are referenced. When you have a standard that's referenced, the question may be, well, is there a date with that reference? So, for example, the PPE category table for AC systems references IEEE 1584 Guide for Performing Arc Flash Hazard Calculations, except it doesn't tell you which date, which edition to use. And this is fairly common. So there's language now that if the date is not provided, whichever edition is the latest edition, that's the one that is being referenced. So with IEEE 1584, there's 2002, there's 2018. Without a date, it defaults to referring to the latest, the 2018 edition. Definitions. Traditionally, definitions were in the .2 of NFPA 70E and actually even of the National Electrical Code in .2 of each specific article. And then over time, if definitions appeared in 2 or more articles, they would move to Article 100. But if a definition appeared just in one article, it would stay in that article. That's all changed. So what has happened now is we have definitions that were still in the 300s, and they were only applicable to the specific article. They didn't span multiple articles. But now that doesn't matter that they don't span multiple articles. All definitions are required to be in Article 100, the definitions. And what happens now is if there is a definition in Article 100 and it is only unique to one specific article, then that definition is going to be followed by the article in parentheses. So for example, battery effect, it was in 310.2. Now it's been moved to 100. It's still only applicable to 310.2, but it is followed, as you can see down towards the bottom, by the article that it is used in. There was also another change in definitions. Some of the definitions had sort of an odd wording. So for example, boundary, arc flash. Well, we know that means arc flash boundary. To assist in electronic searching, this will also now be followed by the way that we would actually refer to it as arc flash boundary. And that's to assist with the searching, the electronic searching. Leather protectors, as I mentioned, the term leather has been deleted. It's just protector, and it's a glove or mitten to be worn over rubber insulating gloves. And so it was just to add clarity since leather was too specific and non-leather is overly broad. So it's just referred to as a protector. 2 new additions to the definitions: ionizing radiation and non-ionizing radiation. These are specific to Article 340, but they have to be in Article 100 now. 340 will be in parentheses. Article 110. Many of you may remember when we went from the 2018 to the 2021 standard that Article 110 had a major reorganization. And the reorganization, there were different sections added, things were moved around, and we actually had a lot more sections when all was said and done. Now it's going back the other way. There's another reorganization, and things are being consolidated and moved around. So that's what I want to show you next about Article 110, the reorganization of this. The first thing to notice is there's a scope. This is one of the articles that didn't have a scope before. So there is a new scope. This article covers the general requirements for electrical safety-related work practices. The reorganization back in 2021, we had 110.1, priority. Now, you may remember that priority, it was originally introduced in Article 105, and it is the most important part of electrical safety. The priority is establish an electrically safe work condition. That's number one. And then it was moved to 110.1, the very first section in 110, because of its importance. The first thing you're going to see is about the electrically safe work condition. Well, because we now have a scope that occupies 110.1, it had to move. So it's now in the second position. It's moved to 110.2, and it has combined with the electrically safe work condition policy. So 110.2 actually has 110.2A, 110.2B, and 110.2C. So these first two on the left make up the 110.2A. And then we have the electrically safe work condition and the energized work. This is 110.2B. When required. When do you have to have an electrically safe work condition? And then 110.2, the general requirements, that's what makes up 110.2C, the requirements until you've established an electrically safe work condition, just referred to as requirements until established. The electrically safe work condition, 110.2A, is now called policy. And an employer shall establish, document, and implement an electrically safe work condition policy that does both, two things. So it does both of the following. Number one, requires hazard elimination to be the first priority from 110.1 is where that originated, and complies with 110.2B when required. 110.2A1 requires hazard elimination to be the first priority. This is a carryover. This started in 105, then it went to 110.1. Now it's 110.2A1. There was an informational note that was added to 110.2A2, and the informational note is that the electrically safe work condition policy could be documented in the employer's electrical safety program or in the employer's management system or similar documentation. There's also a revision. It's really kind of a text revision, and this is when required. Normal operation of electric equipment. It used to be referred to as normal operating conditions, and it was changed to normal operation of electrical equipment. Now, this is where you find the 6 conditions that define the normal operation of electric equipment. There's been a 7th condition that's been added to this, and that is that the equipment is rated for the available fault current. So what we had previously in 2021, it was referred to as normal operating condition, and we had the 6 conditions that had to be satisfied. The equipment is properly installed, properly maintained, used in accordance with the instructions. The doors are closed and secured. The covers are all in place and secured. And there's no evidence of impending failure. Now, this, you may or may not know this, this actually had its roots back in the 2009 edition of NFPA 70E. And you might think, I don't remember that. What's 2009 have to do with this? Well, some of you may recall 2009, that edition is when the definition to arc flash hazard was changed. It used to be the arc flash hazard was defined as when you have exposed, energized conductors or circuit parts. And in 2009 was the edition referring to interaction. If you're interacting with equipment in such a way that could possibly create an arc flash, I kind of paraphrased it. And that really set off a lot of confusion because interaction, what do you mean? So like, for example, if I just have a simple switch like this, that's interaction. Did that mean there's a possible arc flash hazard? Actually, in 2009, yes. And this really caused some confusion. So in 2015, the first attempt that something like we have here was created. And if you're just going to operate the equipment, let's have a checklist. If you can check all 6 boxes, then yeah, okay, go ahead and operate the equipment. That is what it is designed for. Well, now there are some changes to it. And this is part of 110.2, electrically safe work condition, B, when required exception number 1. The new addition was that the equipment is rated for the available fault current. So, for example, if you have equipment that has a certain interrupting rating, National Electrical Code requires that the equipment has to have an adequate interrupting rating, and now you see that in NFPA 70E. It doesn't specifically state, the National Electrical Code requirement doesn't specifically state that you have to perform a short circuit study, but it kind of implies that you do, to verify that the equipment has an adequate interrupting rating. So carrying this over to the conditions, we have a 7th condition now. You may be thinking, why is that such an important issue? Because picture this. So you have your device, you checked all 6 boxes, and you're getting ready to operate it. Well, if the devices do not have an adequate interrupting rating, what if you energize it and there's a fault somewhere downstream from here? And the fault current flows through this device, and you're right in front of it, and the equipment's not adequate. What would happen? Well, it could be a catastrophic failure, and you're right there. So this 7th item was added that when you're checking the boxes, someone has to assure that the device has an adequate interrupting rating. The fault currents vary all over the place, because it's based upon voltages and system impedances and transformer impedances, conductor impedances. It's based on so much data. And the available fault current, it is going to be different at each equipment location. This is part of what drives the incident energy calculations in an arc flash study. You have the clearing time, how long it takes a device to operate, but you also have the magnitude of fault current that goes into this. Going back to our now 7 items that we check, the 7 conditions, no evidence of impending failure. This is one that still will sometimes have people scratching their head, like, how do I know if there's a possibility this failing or not? Well, there's a lot of judgment that goes into it. And I always use the famous phrase, if you see something, say something, meaning if the equipment is buzzing or it's unusually hot or just, something obvious that this doesn't seem like it's right, well, check into it. I don't think you can check that box. So if you see equipment, for example, that looks like this, I'd be a little hesitant to do anything with this. So there was a new informational note, and the informational note references water damage. So evaluating water damage for electrical equipment, there is a reference to a standard on how to do this. And water damage can be quite amazing. I took this photograph several years ago. I'm a big Formula One racing fan, and this was in Austin, Texas. They have the F1 track there. And this particular race was right at the end of a hurricane that came through. So it was the wettest race I think they ever had. What really puzzled me is who would locate electrical equipment in the middle of a drainage ditch. That doesn't seem like the best thing to be doing there. There's another exception that permits the operation of an energized disconnecting means to establish an electrically safe work condition and return it to service as well. And the equipment supplying that disconnecting means or isolating element is not required to be placed into an electrically safe work condition. It's just a little bit of a clarification. So if you operate this device down here to establish an electrically safe work condition, it simply means you don't have to do it up here as well. There was an additional clarification regarding the 50-volt threshold. Equipment operating at less than 50 volts, there's additional language where the capacity of the source and any overcurrent protection between the energy source and the worker are considered, and it's determined there won't be any increased exposure to electrical burns or to explosions due to arcs. So what this is about, 50 volts has been the threshold. It's in OSHA, it's in NFPA 70E. But the concern is, well, even though it's below 50 volts, is there enough thermal energy that could cause a burn or some type of a hazard or an injury? So, for example, this photograph right here is exactly that case. This was actually my son's finger. who went through this. It wasn't a major burn, but hey, it happened. So you'd like to avoid this kind of a thing. Job safety planning, an addition here as well. So the job safety planning completed by a qualified person, and it has to now include an emergency response plan. An emergency response plan. If something goes wrong, you don't have time to try to figure out what to do. You're just reacting. And rather than reacting, have a plan in place as part of the job safety planning. Qualified person. There's some minor changes here. Qualified person, there was the word special. It was changed to applicable. And where that is located, such persons shall also be familiar with the proper use of, instead of special precautionary techniques, it's applicable precautionary techniques. It's a little more descriptive, the techniques that are going to be applicable. Another change, this is about mandatory language. The word can was used when it should have been shall. Shall is the mandatory language. So a person can be qualified for certain equipment and tasks to be performed. And this just says, no, it's mandatory. So it's going to be shall is the word that we're going to use. Article 120, establishing an electrically safe work condition. This is the most important part when it comes to electrical safety. Eliminate the hazard. Establish an electrically safe work condition. 120.5A1, locating sources. There's a new informational note that states locating sources of supply could include identifying situations where a neutral conductor continues to carry current after the phase conductors have been de-energized. So this was added just due to a potentially hazardous condition that could be overlooked. As part of lockout tagout, the stored energy, mechanical energy can involve more than springs, so there was additional text that was added. The complete text now states other sources of stored energy shall be blocked or otherwise relieved to the extent that the circuit cannot be unintentionally energized. The process of establishing and verifying an electrically safe work condition. Hopefully all of you are familiar with this process. It's a whole checklist. And one of the final steps in this checklist is to verify absence of voltage, typically using a portable test instrument. And so there was a bit of a clarification with this one. So what happened, the clarification, is you use an adequately rated portable test instrument to test each phase conductor or circuit part to test for absence of voltage. That's what's already there. There was additional language that states at each point of work. At each point of work. The intent of this was to make sure that if you're going to be conducting work on, let's say, this particular panel right here, then you don't test what's upstream to test for absence of voltage. You test locally. So it just simply means, okay, you're going to be working here. This is going to be electrically safe. Test at the point of work to make sure that it's electrically safe. It's very simple. But it was a clarification that was helpful, that was needed. And so looking at it in a little more detail, what we have is if you were going to be conducting work at panel PP1, and this was to be electrically safe, then you test at panel PP1, not upstream. I mean, you could test upstream if you want, but that's not going to be used to verify absence of voltage at PP1. Work involving electrical hazards. The tables that contain the limited and restricted approach boundaries have had some modifications to them. And I'm going to go over these with you. One of the modifications is the restricted approach boundary. And I would get this question a lot, that OSHA has what are referred to as minimum approach distances, which are pretty similar to the restricted approach boundary, similar intent, similar meaning, but the numbers were a little bit different. And it was always, why is that? So there was a modification to the shock boundary tables, table 130.4EA and B for both AC and DC tables. The restricted approach boundaries, they were revised for the AC table to correlate with OSHA's minimum approach distances. And there were some minor modifications in column 2. That is the limited approach boundary for movable conductors. And that was to address rounding error. Let me explain what's going on here. So this was the table as we knew it for 2021. This is an excerpt of it. And if you look under the limited approach boundary, the exposed movable conductor, you see there was 10 feet, and then the metric was 3 meters. Well, it turns out 10 feet is actually 3.048 meters. And you might think, so we're addressing rounding. That's correct rounding. 3.048, if you round it properly, it would be 3 meters. Well, yes, mathematically that's true, but it introduced a bit of a problem. So this is what we have today. First off, you notice up at the top, it's not shock protection, it's electric shock protection to adhere to the global change that was made. And these two rows here were actually divided. It used to have 751 volts to 15 kV. Now it's split 751 to 5 kV and 5.1 to 15 kV. This is where the rounding was corrected. So yes, 10 feet is 3.048 meters. Yes, if you properly round it, it's 3.0. But here's the problem with that. You're rounding down. And by rounding down, you're missing 0.048 meters, 4.8 centimeters. Even though that isn't that large, that's part of the required boundary. And all of a sudden, we're just going to get rid of it. So the thought was, well, rounding down probably isn't the best thing to do for that since that little bit of distance is important. So instead it was rounded up to make sure that we have at least that distance, and actually now just a little bit more because of the way this was rounded. So that was one of the changes. And then over here, the restricted approach boundaries, these were modified a little bit to harmonize with the minimum approach distances within OSHA. And then there's a new note that was added. And this note is about elevation. For higher elevations above 3,000 feet, you may want to consider modifying or adjusting the restricted approach boundary. Why would you do that? Adjust the restricted approach boundary? Because at higher elevations, the air becomes less dense. So the dielectric strength of air becomes lower as the air density becomes lower. And a lot of electrical equipment does have derating factors once you get above 3,000 feet. Doors do not offer protection. We're going to see that here in a moment with a couple of videos that I have. Estimating the likelihood and severity, there was an informational note about the doors not offering protection, but it was with the DC material. Well, this actually applies to both AC and DC. So the note was relocated. We have an informational note that states, in most cases, closed doors do not provide enough protection to eliminate the need for PPE. In fact, what happens when you perform an arc flash study, incident energy analysis, IEEE 1584, the calculations based on that standard, they assume that there is no door, that the door is wide open, because you just don't know. Unless the equipment is specially designed to keep the door closed and contain the energy like arc-resistant equipment, you don't know if the door is going to stay closed. It might, but it might not. Let's take a look at the video from one of the tests that I conducted a while back in the lab. Okay, let's go. 600 volts. 3, 2, 1. Fire in there. And the door does not offer protection. That was, it wasn't that much fault current. As I recall, I think that was 18,000 amps. I have one more video to take a look at here in a moment. But as I recall, I think it was 18,000 amps. And that was a small little bus plug. What it did is it actually sheared the hasp off so that the door actually broke what was holding it, and it just came blowing right open. I mean, can you tell if a door is or is not going to blow open? There's no way to know. So that's what this note is about. So I have one more to show you of a motor control center. Okay, test 27, door closed. 2, 1. So much for the door being closed. I have a keen perception of the obvious with both of those. The doors aren't going to offer protection. It's like, well, yeah. I was just to illustrate that, yeah, sometimes the doors will blow open and you just don't know. So that's what was behind this note that was added to NFPA 70E. Moving ahead, table 130.5C, estimate of the likelihood of occurrence of an arc flash incident for AC and DC. Just some language change. This was changed to operating condition, and it's just to coordinate with the changes that were made in 110. So this is now estimate the likelihood of occurrence, and the language change is operating condition. The language change here is to change from equipment condition to operating condition, and also the reference was changed because of the renumbering in 110. And this is just simply referencing these 7 conditions that we were already discussing. The incident energy analysis, NFPA 70E, says this needs to be reviewed if there are changes that could affect the results. So the incident energy analysis shall be updated when changes occur in the electrical distribution system that could affect the results of the analysis. There's a new informational note that was added to this. And the informational note lists examples of changes that could be made by the electric utility or other entities. So when someone is performing an incident energy analysis, it's going to be based on IEEE 1584, and that's how you calculate the incident energy. I mean, realistically, most people are going to use software, but the software uses the model from IEEE 1584. And there's a lot of data that goes into this, including the source data, the short circuit data. So if there are changes that could cause major changes within the study, those need to be addressed. So the new informational note, changes that could affect the results of the incident energy analysis by the utility, transformer sizing, modification to protective devices, changes to protective devices, and then I have my change. Officially, this is not in NFPA 70E. Maybe it needs to be added next time. But I'm going to describe this. This is based on my experience in a past life with the utility, that if the utility reconfigures or has major substation additions, it's not on the list. Here's what we're looking at. Let's say that there is an arc flash study, and the calculated incident energy at a given location is the number on the left, 4.5 calories a square centimeter. Great. Okay, so there's a change. Somebody reruns the study and finds out instead of 4.5, it jumps to maybe 5.4 calories a square centimeter. So what? If you wear an 8-calorie PPE, I wouldn't consider that the end of the world. 8-calorie PPE is still going to work, 8 calorie per square centimeter PPE. Now, the arc flash boundary may increase a little bit, and I'll show you how you can get around that. Now, what we're really looking at, the concern is if the incident energy changes enough where the PPE that was specified is no longer adequate. So if there's a change where this goes from 4.5 to, let's say, 16.2 calorie per square centimeter, that would be a problem because the 8-calorie PPE would no longer be considered sufficient. What can cause changes like this? Well, the reference to transformers. Transformer impedance. We have a 1500 kVA transformer on the left using the impedance and the secondary voltage. The fault current on the secondary would be in the neighborhood of 30,000 amps at 480 volts, maybe a little more, maybe a little less, but in the ballpark of 30,000 amps. If that transformer size is increased, then the fault current would also increase to 50,000 amps. Could that affect the incident energy? But absolutely. It'll affect it as the fault current goes up, assuming the arc duration is the same for each case. Then 50,000 amps would lead to a larger incident energy. Now, the opposite could have some interesting effects. If for some reason there's a large transformer and for whatever reason equipment is maybe located where there's a smaller transformer, then what could happen is with the lower short circuit current, a protective device may take longer to operate, and that's always a concern. People think about, maximum fault current, that could be really bad. Well, for a short circuit study, yeah. But for an arc flash study, people get concerned about what if the arcing current drops and now a device, instead of operating instantaneously, operates in the time delay region. So a case in point right here, let's say there's a location where there's 30,000 amps of arcing short circuit current. This time current characteristic indicates that this device should operate in 5 electrical cycles. I should note it's 5/60ths of a second because I know people from other parts of the world have 50 hertz systems. So 5 electrical cycles based on a 60 hertz system, that's 0.083 seconds. But if the fault current were to drop, maybe because of a transformer, maybe a transformer is taken out of service. You have 2 transformers in parallel, and maybe one is taken out of service. The fault current drops. This device will now take a lot longer And the arc duration has a large, very large impact on the incident energy. Sometimes people will question, well, I don't actually know the actual fault current from the utility, or it could vary or something like that. So for years now, I've been advocating, in that case, it's not a perfect answer, but perhaps use an iterative kind of an approach. What that is, you begin with the initial fault current, basically the highest fault current, and you conduct your study, and you'll get a resulting incident energy. And then take that fault current and reduce it in incremental steps, 5 or 10%. What will happen is you'll see the incident energy also reduce. And you continue to reduce the fault current. The incident energy continues to reduce. And you might think, what's the point of this? What's going to happen is you're going to reduce it one step too many, and you're going to see the incident energy make a very large increase. What you've done is you've defined a range of fault currents where the PPE that you want to use is acceptable, and you've identified how low this can go before you start to have trouble with device operation. Not a perfect answer, but at least it'll give you a range. I mentioned utilities making changes. So back in a past life, this is back in the 1980s, I was in the transmission planning department of a really large utility back in Ohio. And I was responsible for about a third of the system. And as part of this, there was an area in the service territory that had explosive load growth. It's actually where I lived at the time. And in the planning department, we ended up coming up with plans for a new substation to support the area. Well, I eventually moved on and headed up the transmission short circuit studies group for the whole system. When this substation that I'm showing here came online, the fault current in the area jumped dramatically. And that could have an impact. It could have an impact on equipment duty. It could have an impact on the incident energy. But also, there were cases in the area where we would retire substations that were old, and you could see fault currents reduce as well. So there are a lot of moving parts to an incident energy analysis, including the device settings. If we have a device with this current and these settings, and then the settings change, guess what? The duration increases dramatically, and the corresponding incident energy increases dramatically. I have a course on arc flash studies, IEEE 1584, calculations, all the details. And I hold this class a couple times a year. The next offering is going to be in December. And so if you have an interest in learning probably more than you ever care to know about IEEE 1584 and arc flash studies, mark your calendar. That's going to be coming up December 4th through 7th. I do it in 2 2-hour segments each day since it's streaming, so you don't have to stare at a screen all day. And there's also an on-demand version of this as well, where it's just in modules. You take it at your own pace, take a quiz, and receive continuing education credit. Equipment labeling. The requirements for equipment labeling have really not changed much in the last several editions of NFPA 70E. On the label, you're required to have the system voltage, the arc flash boundary, and a method to identify the arc flash hazard, or the PPE, which could include the incident energy and the corresponding working distance, the PPE category, not both, the minimum arc rating of the clothing could be used, or a site-specific level of PPE. So as a minimum, the label may look like this: the system voltage, the arc flash boundary, and then a method to identify the PPE, which in this case is the incident energy and the working distance. Well, there's a new addition. And the new addition is the label shall be of sufficient durability to withstand the environment involved, because it can be difficult to read worn labels. So as an example, watch this label fade before your very eyes. All of a sudden, you're not going to be able to read it. That's the problem. Over time, labels can fade. I have an alternative labeling method that I've developed years ago. I have had an article published on this, a video, and the industry has actually been embracing this method. And here's what it is. For the arc flash boundary, standardize on a boundary. 10 feet, for example, for low voltage. Put the word standardize there because the true boundary is 1.2 calories a square centimeter. Someone may say, hey, it's 10 feet where you actually have 1.2. Well, no. So put standard there, and then just list the arc rating of the PPE, because that's all you really need. The end user, they don't care if you have 5.2, 2.6, 3.8 calories a square centimeter. For the person performing the work, they just want to know what to wear. So 8-calorie PPE, keep unprotected people back 10 feet. What's really nice about this is when you go back and perform the review of the arc flash study, what you're really doing now is treating it like a short circuit study. As long as the calculated arc flash boundary is still less than 10 feet, as long as the 8-calorie or whatever you have listed arc rating is still sufficient, you're good to go. You could place a maintenance sticker on it that just acknowledges, yes, this has been reviewed. It is still current. There is this ongoing issue of establishing an electrically safe work condition, especially when you have extremely high incident energy values. And the issue is, an extremely high incident energy value, okay, we better establish an electrically safe work condition. But we need PPE to do that because we assume that it is energized until we've established absence of voltage. There is arc-rated PPE out there with very high arc ratings. This one is 140 calories a square centimeter on the right, but most don't have this. So there was language introduced in the 2021 edition of NFPA 70E that provides risk reduction methods that can be used when commercially available PPE doesn't have a sufficient rating when you're testing absence of voltage. There was a modification made to this language. This is the note providing examples of risk reduction methods. And the first method, this is the one that was modified for 2024. It said non-contact proximity test instrument. It referenced low voltage transformers. Some may know this as PTs, potential transformers, and referenced up to 1,000 volts. Well, the 1,000 volts went away because this is not unique, whether it's above or below 1,000 volts. And the reference to the voltage transformer went away. But instead, it now states use of a non-contact capacitive proximity test instrument or permanently installed metering device, and the 1,000 volts went away. Items 2, 3, and 4 remain unchanged. Hearing protection. This is kind of interesting. So with hearing protection, you're required to wear hearing protection whenever working within the arc flash boundary, but it was recognized you don't necessarily have to be working within the boundary. Just being within the arc flash boundary presents the hazard. So the term working was removed. So basically, if you are within the arc flash boundary, whether you are working or not, you have to have hearing protection. And sticking your finger in the ear doesn't count for hearing protection. Maximum use voltage for rubber insulated gloves. So there's a table that provides maximum use voltage. And this table also referred to something known as the gauntlet. And the word gauntlet wasn't widely understood. What the reference was about was the distance. I'll show you right here. It was the distance from the protector to the cuff right here. And it's important that you have a certain distance, and those are defined in a table. Otherwise, if the glove was shorter than the protector, you wouldn't know where your electrical protection ends. Like, I don't know if it ends here or if it ends here or where that is. So there's a certain distance that has to be visible right here. And the term gauntlet was used for that, which is a little confusing. Some may just know the gauntlet as, oh, throw down the gauntlet. That's probably the way that most people are familiar with this term being used. But this table, it was modified. Distance between gauntlet and cuff was just changed to make it a little clearer. Distance between the protector cuff and the rubber insulating glove cuff. So it's just a change in the way that's described up here. PPE categories for DC systems. DC continues to evolve. And with DC, when it comes to arc flash, there is a table in NFPA 70E. In 2021, there were actually two tables. There was a table from 100 volts to 250 volts, and then there was another 250 up to 600. Well, the table from the 100 to 250 was removed because recent test data shows the probability of sustaining an arc for 125 volts DC is minimal for fault currents less than 17,000 amps. Now, I have to clarify, this is not based on IEEE 1584 data. This came from another source. But because of this data, stating the probability is pretty remote for sustaining an arc flash, we now just have one table. This was the table that we had, the table that was 100 volts to 250 volts. This was removed, and now we just have the table that has been reapplied, repurposed for voltages greater than 150 volts up to 600 volts. And we have the 4 different categories here. And down at the bottom, it should be noted, down at the bottom here, there's a 2-second duration referenced. What that's all about, that comes from IEEE 1584. IEEE 1584 suggests if you have a long duration, an unusually long duration, or no protection at all, if there's room to escape, it may be reasonable to assume that the person will be gone within 2 seconds. Basically, if there's a boom, you're jumping out of the way. Now, don't confuse this, because I've heard people say, oh, the 2 seconds, that's the maximum arc duration. Not really. I mean, will the arc last 2 seconds? I don't know. Could it last longer than that? I don't know. This is just meaning that whoever's there, they're going to be out of the way within 2 seconds. That's what this is about. It's about really reaction and response time. We didn't lose you. Let's say the power goes out. So the power goes out. What do? Well, you try to determine why the power went out. Did a protective device trip? What do you do if the protective device trips? Well, most are going to say reset it. And there you go. NFPA 70E has a different view of this. NFPA 70E, it's referred to as reclosing circuits after protective device operation. There is now a reference to a qualified person and repetitive. Repetitive was removed. Let me explain why that is. This is the language that we did have. There was no reference to qualified person, and down at the bottom it says the repetitive manual reclosing is prohibited. What is that all about? Well, the reason repetitive was removed is it implies, well, I'm not going to do this repetitively. I'll just do it once. And the thought was, well, no, you shouldn't do it at all until a qualified person has determined why this is tripped. So the language now, as a qualified person determines the equipment and circuit can be safely re-energized. Manually reclosing until it's been determined why the device tripped is prohibited. Now, there was some text that referred to an overload. If it was caused by an overload, then you don't have to examine before re-energizing. This was removed from the main text, and it's now referenced as an exception. Article 320. So Chapter 1, that's the bulk of the safety practices. Chapter 2 is more about maintenance. There weren't any real major changes in Chapter 2. Chapter 3 has different articles. There were some changes to some of the articles in Chapter 3, beginning with Article 320. Article 320, there was a modification to the scope. And the modification was storage batteries that exceed 100 volts or exceed a short circuit power of 1,000 watts. That could cause burn injury. It was 50 volts. It is now 100 volts. Why? Well, there's a couple reasons for that. The energy thresholds were also modified. That what we have now is the energy thresholds, DC 100 volts and 40 milliamps, and then the thermal hazard, 1,000 watts of short circuit power. Let me explain the 50 and the 100 volts. So what happens is OSHA has the threshold of 50 volts. Chapter 1 has the threshold of 50 volts for everything. DC, there's been a lot of research and work that shows the actual threshold is 100 volts. It's the United States Department of Energy that has determined that. So the first change that we looked at in the scope going from 50 to 100 was because the thresholds were already at 100. So the scope is 50, the thresholds are 100 in Article 320. So we had to sync that up. But the other is Chapter 3 is for special equipment. And the requirements of Chapter 3 are in addition to what you see in Chapter 1. And it could actually modify the requirements of Chapter 1. So even though Chapter 1 says 50 volts, when it comes to DC, 100 volts is referenced. And you see that throughout the articles in Chapter 3 when it comes to DC. So we had this change. In fact, with DC, on my website, brainfiller.com, I have many on-demand classes, just self-paced classes, module classes. And I developed a class a couple months ago on DC electrical safety. It's a 2-hour class. And this particular class, if you're trying to learn quickly the fundamentals of DC electrical safety, including the 50 volts versus 100 volts, battery systems, data centers, things like that. It's a pretty good crash course. Safety-related work practices for lasers, Article 330. Same kind of a thing here. The hazardous energy, this was modified. In fact, what happened is the hazardous energy for capacitors was greatly enhanced. Less than 100 volts and greater than 100 joules. As long as those values are not exceeded, you're good. If those values are exceeded, you have to have appropriate controls in place. Greater than 100 volts and greater than 1 joule, as long as you don't exceed those, you're good. Once you exceed them, you're not. And then the last one, greater than or equal to 400 volts and greater than 0.25, that's another electrical hazard threshold that if you exceed it, you have to have appropriate controls in place. Article 340, the scope was modified. The scope refers to power electronic equipment, including the following. And it was a pretty good list that's been expanded. We now have generators producing sub-RF and RF fields, ionizing radiation field generators, non-ionizing radiation field generating equipment. And then there's some items underneath number 8. So the scope was expanded. 340.2, the definition of a radiation worker, well, that was deleted because the style manual states that if you have definitions, but they're not used anywhere, then they don't belong in the standard. And if it did remain, which it didn't, but if it did remain, it would have moved to Article 100 anyway. There are many, many informative annexes, and I just wanted to point out a couple of things here with the informative annexes. Informative Annex O, employee safety-related design concepts and facility owners' responsibilities. There was a list, additional safety by design methods, and there's a new item added to the list, and that is installing high impedance protective test points for voltage measurement through the door, such as this type of device. You have a test point that is through the door, so that way you can measure absence of voltage without exposing yourself directly to the equipment by opening up the enclosure. There's another standard, and this really isn't part of NFPA 70E, but I just want to mention it more as for your information. And there's a standard, it's called IEEE 1814. It's under development. It's quite a ways away from being completed. But when this is completed, it's going to be recommended practice for electrical system design techniques to improve electrical safety. So it will basically complement what's in Annex O. There's a new annex, Informative Annex S, assessing the condition of maintenance. You see the term condition of maintenance used a number of times through NFPA 70E. The equipment shall be properly maintained. You assess the condition of maintenance. Well, how do you do that? So Annex S was added to give guidance for assessing the condition of maintenance. Annex S, it's made of many items. S.1 is the introduction. S.2 is assessing the risk. S.3 is providing a visual inspection. S.4, periodic testing and inspection. S.5, permanently installed monitoring. And this may even include something known as CTM, continuous thermal monitoring, which is where you're continually monitoring the temperature of components instead of an occasional IR scan on a regular basis. This gives you more of a continuous thermal monitoring. S.6, predictive techniques. 7, maintenance history. And S.8, standards for electrical equipment maintenance. Of course, it references NFPA 70B, but keep in mind there are also NETA standards that are out there that have been around for a very long time when it comes to testing and maintenance. We're just now rolling out 2024. We're learning about the changes to 2024, but it's hard to imagine 2027 is right around the corner. I want to go over the schedule for 2027 so that you can become involved with this. The first draft, there'll be a public input closing date, June 4th, 2024, less than a year away. This is your opportunity. If you believe there should be changes made, new additions, deletions, submit it as public input. And there'll be a first draft report, and that'll be March 25th, 2025. Then the second draft, there will be a public comment period. The closing date is June 3rd, 2025, followed by another meeting of the NFPA 70E Technical Committee, which will lead to the development of the second draft report. And that'll be posted March 3rd, 2026. I know it seems like, gee, that's quite a few years out there. But as you know, things happen rather quickly. Time flies. Then we have the Motions Committee report, the NITMAMs, and the posting date for these will be May 12th. So sometime after May 12th, 2026, we will see the next edition, the 2027 edition of NFPA 70E. I'm going to break it open to a little bit of Q&A right now and scroll through. Wow, a huge list. I'm not going to be able to get through all these, but I'll scroll through them here. And, appreciate all of you being online. So bear with me for a minute. This is going to take a moment to scroll through some of these. Would opening or closing a breaker fall under normal operation? Well, if you could check all the boxes, yeah. But then what about resetting a trip breaker? Would that be normal operation? No, it's not, because something happened. If a device tripped, the question is, what's wrong? And so unless it was an overload, a qualified person has to determine, why did it trip? Is there a fault? Did something happen? I remember way back, this goes back to the 70s. I'm that old. Back to the 70s, I had a co-op job at a foundry. And there were some people, there were woodblock floor in the foundry because it was a brass casting foundry. So you have to have the block because the castings can get banged up if they fall. And there were some people drilling through the wood block to try to mount something. What they didn't know was there was conduit right underneath it. The lights went out. And had they not been coordinating all this, like, oh, the lights went out, I better go reset the breaker. Well, you close right into a fault. So it is likely to be basically abnormal when a circuit breaker trips. It's actually not one of the boxes that you check as far as being normal. So no. This is a long one, so bear with me. How does one know if the equipment has an adequate rating when performing any work in the equipment? Over the years, we've noted plenty of underrated equipment in use, installed and certified. Let me back up on that. Over the years, we've noted plenty of underrated equipment in use, installed and certified installation years prior. Is there a change in the standard to label such equipment nowadays? Oh, okay. So basically, let me paraphrase this. This comes up a lot. So basically, the question is, if you find that you have underrated equipment, how do you address it in an arc flash study, if I understand the question properly? Keep in mind, this is not a recommendation. This is just based on a lot of information. So if you're performing an arc flash study and you come upon equipment that has an inadequate interrupting rating, that's going to be a problem, because you know that it has an inadequate interrupting rating, which is a code violation. And if something happens and there's a failure and you studied it and you just kind of ignored it, it could come back to haunt you. So there aren't a lot of good options for this. Some will say just don't put a label on it. I don't care for that answer, because if there's not a label on the equipment, did they forget this? Some may put a label on it just as inadequate and some kind of language after that. That's not a horrible thing to do, except the owner's going to be really upset because you've got this big, basically, flag on their equipment. So really, this needs to be documented in the study. And the equipment owner, the facility owner, they need to be made aware of it. That's a difficult one to address. Because again, if you have inadequate equipment, if there's an arc flash, what happens? Regarding testing for hot work, for energized, for energized or absence of voltage, if you're testing for work at PP1, that was the one line that I had, the panel that was downstream, at the location of the work, the panel should still be considered energized if the line side conductors above the main are hot, correct? For 2024, is this assumption still true for the work on feeder or branch breakers that would be de-energized? I believe what you're talking about, I can illustrate that here. I believe the question is, if you try to create an electrically safe work condition, you have the main open here. Isn't this still considered energized? Yes. This may be de-energized down here, but you have exposed conductors. I don't have a main in this, but you would have exposed conductors up here. So for many, that would still be considered a shock hazard, electric shock hazard, and also an arc flash hazard, unless you isolate it with a device upstream. Is an arc flash possible when switching a 480 volt switch to the off position versus turning it back on? that's more of a probability thing. So I think the question is, this isn't 480, but the question is an arc flash possible doing this compared to this? Typically, energizing is considered to be a little more hazardous than de-energizing because you don't know what you're closing into. Did something happen downstream? But although I haven't heard of it happening, I can imagine it could, that if you're de-energizing, if this fails, maybe. But as I said, I really haven't heard it catastrophically failing. Now, there are failures, and I've investigated cases where someone has de-energized, they switch this off. Fortunately, they measure absence of voltage and find out this thing is still energized because the jaws in here failed. But I could picture, be a stretch, but a potential catastrophic failure, although I've never seen one in that case. For the 2-second suggestion, do you need 2 paths of egress? Or could distance away, say 10 feet, be sufficient? Well, the 2-second, it's not really directly about points of egress. The 2-second, and this is kind of from memory, so it's probably not going to be the exact wording, but the 2-second duration or 2-second cutoff is based on if it's reasonable that a person can escape, have room to escape. Now, what that room is, if there's equipment up there, and I have a lot of room back here to the side, if I can get out of the way, somebody's going to make that determination, then you can use 2 seconds. Egress is just, can you get out of the area? Up to what load in kilowatts are arc flash labels not required? There actually isn't any language like that. So arc flash labels, the actual description in NFPA 70E, it states, and again, this is from memory, but it's something to the effect of equipment that such as, and it's a non-inclusive list, switchgear, panel boards, motor control centers, things like that, that could possibly be worked on or interacted with while energized, something like that. You have to have arc flash labels on it. So it's a pretty broad net. Now, some will think, well, we don't do any energized work, so hooray for us. Oh, great. That's exactly the idea. That's priority. But the thing is, in establishing an electrically safe work condition, you're interacting. And you have to verify absence of voltage. And until you verified absence of voltage, you still treat it like it's energized. And if you treat it like it's energized, that means you need PPE, you need to be aware of the hazards. That's on the label. How do you handle testing absence of voltage when there's an incident energy above 40 calories a square centimeter? First off, let me explain the 40 calories a square centimeter. That actually, the don't work above 40 calories, began back in the year 2000, NFPA 70E. The original PPE category tables, they were known as hazard risk category tables. PPE back in 2000 only went to 40 calories. That was the commercial rating that was available, the maximum. And so because of that, there was a note that was inserted that said you need to really consider de-energizing above 40 calories a square centimeter. And that led to all kinds of crazy thoughts about being crushed and launched through the air and just things that didn't quite make sense. But since then, it was the 2018 edition, I think it was, that note went away. And the justification was fantastic. The justification just said 40 calories should have nothing to do with when you de-energize. You should always de-energize. Perfect. But, people still hang on to that 40 calorie. PPE today, what used to be 40 calories as an upper limit, actually, just a moment here. I have it right here. 65 and even 75 calorie PPE has become pretty common. In fact, this is actually a little more comfortable than the old original 40 calorie PPE. So the ratings have gone up considerably with PPE. But anyway, let's say, whatever rating you have, the incident energy is above that. I covered a while ago that NFPA 70E gives you a list of items that you may use to reduce the risk. It's basically, let me do kind of a preliminary test that's not a full contact test, just to kind of give me an assurance that, this probably is de-energized. And that is used like the proximity capacitive test equipment, or if you could visually verify those gaps in the equipment, things like that. Because you do have to verify absence of voltage. And if you have a high incident energy, that could be a problem. And so NFPA 70, it actually started in 2021, gave you some methods where you could try to reduce the risk. I read of a disconnect switch failure in a magazine, one of the main magazines, from a broken spring and or removed barriers. Yes, that can happen. I investigated a case like that where there was a switch and the mechanism failed and it remained in the closed position. The absence of voltage test is what saved them, or a lot of people would have been, well, it wouldn't have turned out well. Arc blast. There appears to be a separation between arc flash and arc blast. Article 360, informative Annex R, that's for capacitors, holds a vast majority of the references within 70E for arc blast. What's the reason for the separation? And are they trying to tie this hazard to capacitors? Okay, so let me explain that, because I have a segment on capacitors. In fact, when I was doing my global tour a couple months ago, I had a big segment on exactly that. So what has happened is Article 360 was mostly from the U.S. Department of Energy, the DOE. And it is specifically about capacitors. And so what they're looking at is the blast. They have lung protection boundary, hearing protection boundary, based on the blast pressure from a capacitor discharge. When you don't have a bleed resistor and a capacitor ruptures or just discharges all at once, you can have a tremendous amount of energy from that. And it'll be a shock wave. And so they have what's called the lung protection boundary and the hearing protection boundary. It's specific to just the impulse, because a capacitor discharge is going to be an impulse. It's not going to be like a 30 cycle or 60 cycle or whatever, like an arc flash. It's just that initial shock like that. And so that's what that's based on. And they have equations in there. And the equations were derived based on using a model from the U.S. Department of Defense for munitions, basically ordnance explosions, where they have modeling for the pressures from that. So they use that methodology to come up with the equations for basically the shock wave, not electric shock, but the shock wave for the blast pressure for the capacitor discharge. So good question. So stay in touch. This is how to keep in contact. There's my email address. LinkedIn, there's actually two. There's Brainfiller, the company. There's Brainfiller me. I have a YouTube channel, and I also have Arc Flash Forum. With that, I really appreciate everybody being online, and I wish you all a fantastic day, or I guess for some of you, the middle of the night on the other side of the planet. But thank you very much. I hope it helps your understanding of the latest and greatest of the 2024 edition of NFPA 70E. Take care. Thanks.